Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to talk about linear systems, which is the fundamental concept in algebraic geometry used to construct maps and also study them using the notion of divisors. The simplest example of that is projection, and that's an example that I want to go through in detail. Okay, so let's have a look at the basic setup for this. I'll do this in the projective case, it's a little bit easier there. So X will be a projective variety, and the key notion that we'll need to introduce is an invertible sheaf, L here. And since it's an invertible sheaf on this projective variety, we know that we can associate to that a Cartier divisor. There'll be lots of Cartier divisors that you can associate to that. But in particular, we can write this out in a specific form, O of D. So this is some invertible sheaf of rational functions. And that's given by this D, which tells you where the poles and zeros of those rational functions are. Okay, so that's our starting point. We also need some global sections, say S0 up to Sn. Each of these had better be non-zero, so we'll make them all non-zero. And if we're given that, at least we'll get a rational map from X to Pn. How does that work? So you've got these n+1 sections of this invertible sheaf here. Then you map any point X to just this ratio inside Pn. Okay, the point with these homogeneous coordinates. So how does that work? So remember, S0x up to Snx, remember this L is a line bundle, so above every point X is a one-dimensional vector space. S0x up to Snx are basically points on that one-dimensional vector space. And so since they're in this one-dimensional vector space, you can talk about the ratios between them, and so it really defines an element of Pn like that. Okay, or at least it defines an element of Pn as long as all these elements in this one-dimensional vector space are non-zero. If they're all non-zero, then this map is not defined at that X, and that's called a base point. Okay, a base point where S0x up to Snx, all of these sections are zero there. And the set of all these base points is called the base locus. So it's not defined on the base locus, okay, but away from this base locus, where at least one of these sections is non-zero, it will be defined. Okay, so that's the basic setup that we need, and that's why we use these invertible sheaves. And the first very important observation is to see what happens when you do a linear change of coordinates. Okay, so let's see what's happening here. Okay, so we need to use matrices, of course, to get your linear changes of coordinates. So suppose you have a matrix A whose entries are A, I, J. So this is an n+1 by n+1 matrix with entries inside K. Of course, that gives you a linear map from n+1 dimensional affine space to n+1 dimensional affine space. So if you look at the projectivization of that, it gives you maps, let's call it phi, depends on this matrix A, from Pn to Pn. Okay, so basically this will descend. Okay, so the only thing that gets mapped to zero here, I guess this is not necessarily defined all the time. Okay, so if it maps some non-zero vector to the zero vector, it might not be defined there. So I guess it's a rational map. So at least you have a rational map like that. Okay, so that's what we have there, a rational map. And so what you might want to do is say, okay, suppose you take this map here given by these sections of this line bundle, that maps from X to Pn, and we can compose it with this map phi from Pn to Pn, right? And of course, this is also given by sections of a line bundle. And what sections are they? Well, actually, they're sections of the same line bundle. And what are those sections? So instead of using S0 up to Sn, you're going to use S1 prime up to Sm prime. And what are these Si primes? Basically, they're just linear combinations of the original Sj's, those global sections here. Okay, and what linear combinations? Well, it's just given by this matrix. And I hope you can see that, yes, this is the type of thing that you would expect. Okay, so if you want to do a linear change of coordinates, say if you're given these n+1 sections, you can have some linear change of coordinates, you play around with them and get these global sections instead. The corresponding map, what is that? The corresponding map is, well, instead of this one here, you just compose with this, you take this map and you compose with this rational map from Pn to Pm. Okay, that's given in this way like that. Okay. So what's the upshot of this? So the upshot of this, and this is kind of important, is that S, for all intents and purposes, this map here, the interesting information is essentially captured just by the span of these global sections, the span of S0 up to Sn inside this vector space here. Okay, so let's just see why that's the case. So suppose you have some invertible linear, this map is given by some square matrix which is invertible. Okay, so what happens there? If you have a square matrix which is invertible, okay, and you do the corresponding change of basis here, so you replace this with some invertible linear change of variables, what happens? Well, essentially, you just compose with, in this case here, will be an isomorphism from Pn to Pn. Okay, so that's the only difference. You just compose with some isomorphism. It is a different map, most likely. Okay, but the thing is that, well, essentially, what is it doing to this x? It's still contracting all the same points, okay, and points which are separate stay separate, okay, in the new coordinates. Okay, so what other things can you do to keep the same span? Okay, so another thing that you can do to keep the same span is you can just add in some extra sections, okay, which are just linear combinations of the previous ones. Okay, so let's see what that does to changing the map that you get. So suppose instead of just having these, you add in an extra Sn plus 1 or some more, which are linear combinations of the original. Okay, so if you think about that, what does that do? So you're basically composing by a map inside here, where essentially you're going into some bigger affine space here. So you're moving into some bigger projective space. So on the first few coordinates, you're keeping it fixed, but you're adding some which linearly depend on the previous ones. So what this map here, in that case, corresponds to, that linear change of variables, is just you're inserting one projective space inside a bigger dimensional projective space in a linear fashion. Okay, and then what is this new map when you do that change of coordinates is that means that you map into this Pn, but that Pn sits inside some bigger projective space. Okay, so that's all you've done. Okay, so really the map is more or less the same. So often when we study these linear systems, we don't really care so much about this, the individual elements inside here, the individual global sections, but rather the space spanned by it. And that gives us the notion of a linear system. Okay, so let's define it formally. So a linear system is basically, you look at some invertible sheaf L like this, you look at the space of global sections, and you just pick some subspace W of that. It's linear because you're looking at subspace of this vector space. Sometimes the term linear system also corresponds to the corresponding projective space P of W. So that's something that we also play around with. Okay, and what is the complete linear system? Okay, the complete linear system is when you pick this subspace to be as big as possible, given the invertible sheaf here, so that means it's the whole of H0 of L. Okay, so why is it that you sometimes look at this instead? So remember, this W is essentially going to tell us about the map, okay, but we want to understand it, and it's really a map, so it should be understood geometrically. So the way you understand it is you look at this P of W. So in this case, let's have a look at this P of the complete linear system. H0 of, remember, the L will be O of D. And one way to write this, remember, is that it's precisely the set of all divisors on X, D prime, such that D prime is linearly equivalent to D, and D prime is effective. And we'll write this set of divisors, okay, this set of effective divisors as this complete linear system like that. So it's got the absolute value sign on the D. So this is just some notation. And this is something that we should think of as being a projective space, okay? So it's a set of divisors. If you have a surface like this, okay, these divisors will be curves, effective curves, okay? And you think of them, well, you know, there's basically a projective space worth of them. So as you move along that projective space, you'll get different curves, okay? And they sort of can roam around in this linear fashion, okay? So let's just have a little think about this point of view. So why is this an interesting thing to look at? So the first thing that, for example, you want to know about this map is what is the base locus? Where is it defined? Okay, so by looking at the base locus, looking at this, you can say where it's not defined. Okay, so this is basically the simultaneous zeros of S0 up to Sn. Of course, if you have something which is 0 at S0 up to Sn, it's also a 0 of any linear combination of these. And looking at that, you can see that, well, if you want to look at the zeros, simultaneous to zeros of all of them, you might as well look at this zeros of the span of them. Okay, and what does the span correspond to? So remember, how does this work? If you have a global section here, what you do is you look at the set of zeros, and the set of zeros, that's going to be an effective divisor, and that's your D prime that you want. So basically, to get the base locus, you look at this projective space worth of divisors, and you intersect them all. You look at the set of all these D primes, you intersect them all, and that's your base locus. Okay, so that's the key thing of how you want to look at this, and that's one reason why you want to look at this linear system from this projective point of view. Okay, so let's have a look at the simplest example of what's going on. Okay, so I want to look at projections. The easiest case to look at will be when you just start with a projective space, P of V star, but also works when you have X is some projective closed subset of P of V star, so that's some projective variety like that. Okay, so the situation we want to look at is we want to pick our D, okay, to be what's called a hyperplane section. So essentially what we do is we have some P of V star here, and we pick inside there any hyperplane that we like, and we pick it so that it does not contain all of X. Okay, so that's something that we need. When that happens, that means that this hyperplane will actually cut the X into something smaller. So if you look at the intersection of H with X, it now becomes a divisor on X. Okay, and we can use that for our D. Okay, so that's kind of the situation that we want to have a look at. Okay, so such divisors, they're called hyperplane sections, and they're also said to be very ample, the ones that arise in this fashion. Okay, so that's another name for them. Okay, so let's just start by looking at this procedure. Okay, in the case where X is, we'll start with the case where X is all of this P of V star. Okay, X is P of V star. We look at some line bundle. The line bundle will be given by this H. So it's essentially the line bundle of variable sheaf is O1. And in this case, what is the global sections of this? The global sections is just V. Okay, so what I'll do is I'll think of this P of V star as just one-dimensional subspaces of V star. Okay, and then the functions on that will be given by V. And so we want some subspace W of that. Okay, and duality says that, well, the subspaces of this here will correspond to linear subvarieties to this P of V star. Okay, so linear subvarieties of that, so P of V star. So how does it work? So basically what you can do is you can just look at all the zeros of this W. Okay, so what are the linear functionals where this is 0? Okay, so if you take a linear functional on which this is 0, by definition this is just something in W perp. So remember, W perp is a subspace of V star. It's all the linear functionals which is 0 on W. So we call this linear subvariety L. Okay, so that's what you'll have here. If this is getting a little bit abstract, I'll do a little example later on. Hopefully I'll make it all become clear. So since this W perp is a subspace of that, okay, you can look at the projectivization of this is contained inside there, okay, and it's a linear subvariety. Okay, so basically instead of looking at one-dimensional subspaces of all of this, you're just looking at one-dimensional subspaces that happen to fall inside this subspace. Okay, so now we can look at this subspace, and it gives you a linear system, and it's a map. It's not completely defined. Basically, you can pick any basis you like for this, and that'll give you a map to, and what is the space that you're looking at here? So in this case, it turns out that the map that you want here is, it'll map to P of W star. Okay, that's the correct thing to do. If you want to do it canonically, that's the way you should do it. Okay, so it's P of W star. So this is the same dimension as W, but this will make it more canonical. Okay, and it's very, very easy to sort of say how this map works. Okay, how does the map work? Okay, so it works like this, and the reason why I've written it out like this is that means that I can say what this map is without having to pick bases and things like that. Okay, so if you want to pick bases and you want to work like this, using this observation and say, well, you know, you can change basis and it does this, that's fine. But if you want to do it canonically, this is kind of the intelligent way to do that to it. Okay, let me show you what happens. So W is a subspace of V. So by duality, that means that W star is a quotient space of V star. So if you have the inclusion map from W into V, you apply the duality functor, okay, so the HOMS into the field K, you get a map from V star to W star, which is surjective. So you can think of it as this quotient. So in particular, if you have any one vector inside here, or one-dimensional subspace here, you can map it over to this quotient, W star, okay? If there's something inside here, you map it over to here, and that one-dimensional space could collapse to something that's zero-dimensional, in which case it's not defined, or it could be a one-dimensional subspace, okay? They're the two possibilities, in which case it gives you a point. Okay, so they're the two possibilities. Okay, so where it collapses, that's the base locus. And where is this base locus? Okay, so there are all the things where, or basically you're taking some linear function here, and when restricted to W, you get 0. So that means they're the things inside W perp. So that is the base locus of this map, is L. Okay, so that's the basic idea of a projection, and this is called projection away from L. So it's not defined on L, okay, but away from L, okay, it's defined and it sort of projects everything away. I'll give you an example which shows you that. Okay, so let's just soup up this picture a little bit more. Okay, so what you can certainly do is that once you have this map, if X is inside here, you can take this projection, PV star to PW star, and compose it with the inclusion from X into P of V star. So you get a map from X to P of W star. And without going in through too much detail, what this corresponds to, if you don't want to work in this sort of setting, okay, you want to work more directly with what we have here, what you can do is you can look at this divisor HX here, and this is a divisor, so it gives you a linear, an invertible sheaf, okay, gives you an invertible sheaf, so you can look at that invertible sheaf, and essentially the global sections of this O1 will map to global sections of O of HX. Okay, there's a map there, and oftentimes that will actually be an isomorphism. Okay, not all the time. Okay, if X is a point, often it collapses, so that's not the case, but often this will be an isomorphism. So essentially using those same global sections allows you to give the map into P of W star like we did before. Okay, so that's what's going on there. Okay, so hopefully this example will make it clear if this is a little bit abstract, okay? So what we'll do is we'll work with the situation X equals P of V star, and that P of V star will just be the projective plane with homogeneous coordinates X, Y, and Z. We're going to pick a linear subvariety in there, which is given by just the point P, which is 1, colon 0, colon 0, the point with these homogeneous coordinates, okay? So remember we're using duality, okay? So what are the global sections of the line bundle we're interested in here? So the O1 here, okay, the global sections are generated by X, Y, and Z. So you want to look at all the global sections which are 0 here, okay? So what are they? Well, certainly Y is in there, okay? The Y evaluated at P is 0, Z evaluated at P is 0, okay? And you can have any linear combination of them, but once you have a linear combination that also includes some non-zero amount of x's, it'll be non-zero. So basically W here that corresponds to the P, so the duality here is that W is just a span of Y and Z. Okay, so that's what you have here. And what's the situation that you have here? So you have the P of V star, so this is P of V star is my P2 with homogeneous coordinates X, Y, and Z. And then now I want to go to P of W star, so W is here, so it's now only a P1 because they're in 2 variables, homogeneous coordinates, so this is P1 with Y and Z. Okay. So if you want to think about what's the map from V star to W star, so it's the span of the X, Y, Z maps the span of Y, Z, where X just goes to 0. Okay, X goes to 0 there. And what's the actual projection? So you can write it now nicely in coordinates here. So I'm going to now pick a basis for this W, which will just be Y and Z. And then I can use that to do what I want. So basically the point X, Y, Z gets mapped to Y colon Z. Okay, that's the map. Okay, that's very simple to write down. Okay, so it's not a complicated thing in any particular example, but it does take a little while to work through for each example from the abstract definition. Okay. Okay, so just have a little think about this. So this is not, so I claim that this is not defined everywhere. So its base locus is just this single point. So let's just check here that this is indeed the base locus. So where are both of these 0? If both of these are 0, so y and z are 0, x you can scale to be 1, so the only possible point is this p. So it's projection away from this p. So it's not defined at the point p equals 1, 0, 0. But it's going to be defined everywhere else. And let's see what the definition is. So basically you want to look at the ratio of y to z. So we can now assume that x is non-zero. Okay. So let's just fix. Let's have a look at this. Okay. So essentially, what is y colon z? Okay. So if you think about this, let's just suppose for example, make x equal to 1. Okay, let's scale it so x equals 1 and look on that patch where x is non-zero. Then essentially all you're doing is you're looking at the ratio between y and z. So you're looking at an affine patch in the y-z plane, and you're looking at the ratio y to z. So basically that's a slope. So if you think about it, okay, what it gets mapped to, any point gets mapped to the slope. And the slope is the slope of what? Essentially, you're looking at lines through this P, and you're going to look at that. What is that slope? So the best way to think of this P1, these ratios, y to z, is it's going to be what P1 is. It's the projective line of lines through this point P. Each of the lines will give you a different point inside here. Okay. So for example, if you look at the case where you have y is equal to 0, y is equal to 0. Okay, you can scale that up as much as you like. That'll be given by a single point. And of course, y equals 0 is some line that goes through this point P here like that. Okay, so this is a set of all things where y equals to y equals 0. Okay, so 0 anything, or 0, 1. Z equals 0 is going to be something like that. And for all the other ratios, you get something else. So basically, the way you want to think about this linear system, okay, this linear system here, so this is all the things, all the divisors, okay, in the complete linear system, it's all the divisors which are linearly equivalent to this original D, okay, and are effective. So that'll be the set of all lines. You get the set of all lines, okay, it's a projective plane of all lines if you look at the complete linear system for this O1 inside P2. But we're not looking at all of O1, we're only looking at the ones inside W. And the ones inside W are which lines? They're just the lines which go through this point. Okay, so that's what's going on. Okay, so rather than looking at the projective plane of all lines inside P2, you just look at the lines which go through that point. And that's going to be a projective line worth of them. So one way to think about the projection, and this gives you the notion of a projection, is where does a point Q get sent to? Okay, it gets sent to this projective line, and the points there are some line through here. And which line does it get sent to? It gets sent to the line which is the line that joins P to Q. Okay, it's as simple as that. Okay, where does a point get sent? Okay, Q. It gets sent to the element inside here, so that's the line through P, which is which line through P? The one that joins P and Q. And this is, of course, very well defined unless Q equals P. If Q equals P, which line are you talking about? Okay, it could be any possible line that goes through P. And that's why it's not defined at P. This is another way to see it. Okay. And the other thing is that this also gives you the idea of why it's called projection from P. Okay, so it's not defined from P, but basically you project away from P. Anything that's along this line which is not P gets sent to the same point, which is this line. Yeah. Anything along this blue line on this D0 where y equals 0, okay, that's not this P, gets projected to the same point. So you project away in that fashion. Okay, so that's the basic theory of linear systems. I guess the most important thing is understanding the base locus, and also setting up this projection is an important example. Or maybe one other thing is to say, okay, so if you look at this linear system here, what is this linear system? If you think of it in terms of the not the vector space, okay, not this vector space, but rather its projectivization, it's a set of all these divisors. So this is the projective space, a projective line of divisors. And if you intersect them, what's the common intersection point? It's just this P. So that's why it's the base locus. That's the other way to see the base locus and to visualize what this map is, okay? So that's how an algebraic geometer visualizes this map, okay? So the other very important question is, well, suppose you don't have a base locus, so it's well defined, okay? The question becomes, well, what is the map doing? And the most interesting case is to say, is it a closed embedding, for example? Okay, so, you know, if it's an isomorphism, that's also interesting, but you want to study things other than just projective space, okay? So you want to say, when is it closed embedding? Okay, so let's look at the proposition which tells us what's when that happens. And I don't want to give you the proof of this, I just want to tell you the statement, but hopefully also make you believe why it ought to be true. Okay, so suppose you're in this setup where you have some invertible sheaf that's given by some divisor D, so OXD. You look at the global sections of that, and you have some linear system given by this W. And we'll assume that this is going to give you a map in the sense that this is base point free linear system, and the map is going to be phi, so this will go from X to P of W star. Okay, so the question is, when is phi a closed embedding? Well, it happens in the only in the if the following two things hold. Okay, this is a criterion, a necessary and sufficient criterion for checking this holds, and this is one that gets used quite a bit. Okay, so the first thing, of course, is that you want that phi is some sort of is injective. That's the first thing you want. Okay, so injectivity. So how do you sort of check injectivity? Well, the main thing that you want to do is you don't want to make sure you don't have a situation of mapping two things to one thing. So the way that's stated for injectivity is that W separates points. This is precisely corresponding to injectivity. So if you have two separate points, P and Q inside X, you've got two separate points, you want to say they don't get mapped to the same point, and that's given by the fact that W separates points in the following sense. It means that if S, there exists an S and an element of W, which will separate the two in the sense that S of P is equal to 0, so it'll be 0 on one, but it'll be non-zero on the other one. Okay. So let's just give an example of how things might separate points. Okay, so let's look at this linear system here, okay, which is the lines through P, and it will separate this Q from this Q prime. Because if you take this particular section, which has a 0 here, it's 0 at Q, but not at Q prime. Okay. However, it doesn't separate this point from another point like this. If you have these 2 points, right, there's only one, up to scalar, there's only one section which is 0 at Q. And that one is also 0 at Q double prime. So it doesn't separate them. Okay, so that means that it doesn't matter what linear combination you have of all the basis vectors inside here, okay, you'll always get the same values, okay, so you can't send these 2 points to different things, okay, and this is an if and only if, and it's not too difficult to think through that and see that, oh yeah, that's what corresponds to injectivity. The other thing that's a little bit hard to say is that unfortunately what can happen is that you can have things which are injective but not isomorphisms, okay, or not closed embeddings. Okay, they can do something non-trivial, and I guess one way to kind of say that, well, how do you make sure that you have a closed embedding? Well, one thing that you might want to do is that if you want to restrict from X to the image, okay, maybe what you want is essentially that it is an isomorphism with its image. And if you start with a manifold and use manifold theory, you'd say, well, one thing to get a diffeomorphism or a biholomorphism, if you're looking at complex manifolds, is you can use the inverse function theorem. Okay, so maybe you could play around with tangent spaces. And that's actually something that will give you what you need. So in this case, you don't want the inverse function theorem, you kind of want to use something like the implicit function theorem. And what you want, you kind of want injectivity on the tangent space. So what you want is W separates tangent vectors. And one way to think about this, by the way, and this is rather neat actually, and you can kind of really make this work in algebraic geometry, is this is the case where you kind of, instead of separating P and Q separate points, you can, in algebraic geometry, formally talk about P and Q coming together infinitesimally. and if they come together infinitesimally, that you get a tangent vector. So this is a certain way is just the case where P equals Q. Okay. So let me give you the definition for what this means for W to separate tangent vectors. So that's the other criterion that you need. It's a little bit hard to describe, but maybe if you see it in an example, you'll realize that actually it's not such a difficult thing at all. Okay, so what happens here? So you kind of want to do a similar sort of thing. So firstly, you mark out where the sections are 0 at that point. So suppose you're looking at tangent vectors at some point P inside X. You pick some P inside X. Okay. So maybe I'll change that. So I'll change that to Q. So as not to be confusing with this P that we're projecting away from. So at some Q. Okay, so what do you want to do there? So essentially, these sections, right, you look at the sections which are 0 at Q, and that makes sense to talk about that. Remember, these sections, if you look locally at a point, well, the line bundle is isomorphic to just functions there, okay, regular functions there. And you pick an isomorphism, and there's a choice up to a unit, but the unit is not going to affect things like, are you in the maximal ideal of functions which vanish there, or its square and things like that. So this MQ, that's the functions which are 0 at Q. If you mod up at MQ squared, remember this is the cotangent space at Q. And what you want is the sections there, the functions there, will actually span that. Okay, so you're looking at the functions which are 0 there, so you're kind of in MQ already. And you want to say that if you look at all of these, you have enough of them that it spans this MQ, mod MQ squared. Okay, so let me just give you an example to show you that this thing, it may look a little bit complicated, but rather than working at that, if you look at a simple picture of what goes on, it's a lot easier, okay? So let's look at the same setup that we have here, but now what I want to do is I want to restrict what we have here to X, which is a conic inside P2. So that's given by this conic here, okay? So we're restricted, okay? Everything else is the same, okay? So if you look at, instead of using this O1, you restrict O1 to this X. So basically, instead of looking at some hyperplane like this line here, you look at its intersection with X. So essentially, you can look at this, the divisor HX here. So if this is Q and Q prime, HX here is equal to Q plus Q prime. Okay? So that's what you have here, okay? That's what you have. You can have OD, okay? X is the conic, and D will just be this Q plus Q prime, or you can pick any these 2 points as well, okay? That's something that you can have. Okay, and you can map the global sections onto the global sections of O, Q plus Q prime, okay? And it turns out that's going to be an isomorphism of the global sections, okay? So, and you can have this map, but of course the map that you get is just the inclusion of X into here with this rational map. Remember the base locus of this map here is just this point P, and if this conic doesn't contain P, well then it's going to be defined everywhere, so it's base point free. Okay, so let's see, for example, that this W that we picked, which is this W, which is a span of Y and Z, does separate tangent vectors at Q prime, for example. So we think in terms of Q prime, here's a tangent vector like this. And so the way you should think about it is as follows. So you look at all the sections which are 0 at this Q prime. Okay, this is this WQ here, okay? Look at all the sections with 0 here, which is basically given by this thing here, okay? This divisor here. So you have some sort of a section which is 0 on this blue line, and it's going to be non-zero to the left and right, so to speak, okay? And kind of see, since it's 0 on the left and right, that means it's going to be non-zero on this vector. So it kind of separates that vector because it is non-zero there, okay? Just as in this case here, if you want to separate Q prime from Q, okay, you can pick a section which is 0 here, but non-zero there. And the idea is if you kind of take the limit as Q prime goes to this, in this case, you're sort of still separating it as long as you know, when the point comes towards here, okay? So you can separate that. Okay, so so that's what's going on there, okay? It separates tangent vectors. So it turns out that if you look at this map, and you're working over the complex numbers, then you have a map of complex manifolds, of Riemann surfaces in fact, and locally here what you will get is a biholomorphic map. Okay, so locally here. But it's not injective, okay, so in this case these two maps get mapped to the same point, okay, but locally you have a biholomorphism. Okay, so let's look at an instance where it doesn't, in this case, separate tangent vectors. So where's that? So what you can do instead is you can look at, draw the point, the line through here, which is tangent to this conic. And you can say, well, does this W separate tangent vectors at that point? And the answer is no. Because now what are the tangent vectors? They're like that. Okay, and you can see, well, what's happening with this section. The section is 0 along here. Okay, so that section is going to be, well, it's non-zero here and here, but along here it's 0. So even on this tangent vector, it will still be 0. Okay, so it doesn't separate that tangent vector. Okay, so in other words, if you have a point coming along this tangent vector in this tangent vector direction, okay, it's going to be 0 there. So it doesn't separate tangent vectors. So this gives you a way of determining whether this map here, phi, is a closed embedding. Okay, so this is rather a very useful tool, because one of the things that you want to do if you want to study some sort of projective variety is you want to say, oh, well, can you map it to something else? Is it the same as something else? And the way you'll do that is you construct a map. Construct a map means you essentially pick some invertible sheaf, or equivalently pick some Cartier divisor D, and then you have to have some sort of linear system. Okay, so you pick some subspace of the global section. Okay, and what I hope to have shown you in this video is that the way you study what this map is also involves looking at this projectivization of this, not only this H0 of L, but more generally this projectivization of this W star. Okay, so you're looking at or projectivization of W. You're looking at this projective space of divisors, and that will really tell you how the geometry works. Okay, so I hope I've shown you that firstly it's easy to see what the base locus is, where this is defined, but also if you want to check things like, oh, is it actually injective? Okay, you can do that by looking at this projective space of divisors. Okay, and also, does it separate tangent vectors? Okay, you can also do that by looking at it visually like that, and that gives you the geometry. I hope you enjoyed this adventure in pure mathematics.